A very warm welcome, my dear students. This question you see has come in CBSE board more than once. And if you don't know the applications of Gauss law, you'll waste 5 minutes on something that should take just 30 seconds. So in this video, I'm covering the 3 applications of Gauss law, which are very important for the board exams. We will also solve the board papers, like we'll solve the past year CBSE questions step by step. So let's get started. So I have already explained Gauss law completely in my previous video, so you should definitely go through it in case you haven't. So the first application we are discussing is the electric field due to an infinitely long straight wire. So let's say I have a straight line charge. You can see over here this y dash. It has a linear charge density of lambda. So what is lambda? It is the linear charge density for this infinitely long straight wire. Further, if I want to find out the field at a distance r from it, right? So first we need to assume a Gaussian surface. Now this cylinder over here is my Gaussian surface. So for this cylinder, I can assume it has a radius r and it has a length L. So as per Gauss law, I already know that the electric flux can be written as the total charge enclosed by epsilon naught. Now in this situation, if my linear charge density is lambda, that means this is the charge per unit length. So if I want to find out the total charge in this situation would simply be equal to the linear charge density, that is lambda, times L. The length of this one over here is L. Therefore, as per the Gauss law, I can write my flux as lambda times L by epsilon naught. Now further, I can open this flux up and I can write it as the electric field times the surface area times cos theta, and this is equal to lambda L by epsilon naught. Now in this scenario, if you look in carefully, my ds is in this direction and my electric field is also in the same direction. Therefore theta over here is 0 degrees. So I will substitute theta as 0 degrees, and we know that cos theta, cos 0 is going to be 1. So now I'm left with E into S. Now S for the cylinder over here is 2 pi RL, because the curved surface area of a cylinder is 2 pi RL. So this E into 2 pi RL is equal to lambda L by epsilon naught. Now if I rearrange this expression, I can simply get lambda L by 2 pi RL times epsilon naught. This L and L get cut. So now I'm left with my electric field as lambda by 2 pi epsilon naught times r. So this is the final expression for the electric field due to an infinitely long straight wire at a distance r from it. Important thing for you to notice over here is that my electric field is inversely proportional to the distance rather than proportional to the square of the distance. So this is only applicable for an infinitely long straight wire. You can learn this expression directly because it's very important. Many a times this expression is directly asked in the board questions, like I had shown you the previous question as well. So this is very similar, and this is something that you need to learn. Now let's move on to our second application, which is electric field due to an infinite plane sheet of charge. Now over here, let us assume that we have a infinitely long plane sheet of charge which is having a positive charge, and it has plus sigma as its surface charge density. Now again we need to assume a Gaussian surface. So in this situation as well, I can take the Gaussian surface to be a cylinder. You can take any other Gaussian surface as well, but cylinder is the most easiest one since it is symmetrical and we can very easily take out the area vector over here. So the cylinder, if you see in carefully, it has this surface, so its area vector would be this way. For this surface, the area vector would be this way. And for this, the curved surface, the area vector would be like this. And since this is a positively charged sheet, therefore your electric field is outwards. Now, carefully, if you look at it, the two circular areas will contribute to the flux, since for them the angle is 0 degrees and cos 0 is 1. But the curved surface will not contribute to the electric flux, since it is making an angle of 90 degrees with the electric field, and cos 90 is 0. So now if I write down the flux, then I know the flux as per the Gauss law is the charge enclosed by epsilon naught. And further, since my surface charge density is sigma, it is basically the charge divided by the area. If I assume that the area of cross section of the circular path is A, then I can write my total charge enclosed as the sigma, that is the surface charge density, times the area. So flux in this situation can be written as sigma times A by epsilon naught. Further, the flux can be written as EA cos theta, and this is going to be equal to sigma A by epsilon naught. Now for the first circular surface, you can see it is electric field times A times cos 0. And then there is another surface for which also we will take EA cos 0. So this would be equal to sigma A by epsilon naught. From here I get 2EA cos 0 is 1 in both situations equals to sigma A by epsilon naught. Now on rearranging this, I get my electric field as sigma by 2 epsilon naught. So this is the electric field due to an infinite plane sheet of charge. Important thing for you to notice here is that your electric field is independent of the distance, shape, size. Now we move on to our last application, that is the electric field due to a uniformly charged spherical shell. So let's say that I have this spherical shell of radius capital R and it has a charge plus Q on its surface. Now for the electric field due to a uniformly charged spherical shell, we will have three different situations to talk about. So let's talk about the first one. In the first one, I want to find out electric field at a point which lies outside this shell. So let's say that there is a point P which is at a distance small r, and the small r is greater than the radius. So basically it lies outside the shell. So let's say that we have some shell over here, like we have a point at a distance small r from it, and we can assume the Gaussian surface over here to be another shell but with a radius small r rather than a capital R. So this dotted red one is my Gaussian surface. Now I know that the flux is going to be equal to the charge enclosed by epsilon naught, right? So we can write this as electric field times the surface area times cos theta equals to the charge enclosed. Here the charge enclosed is just Q upon epsilon naught. Now over here, for a positive charge, we know that the field would be outwards, and we also know that the surface area is also outwards. So over here we have cos 0, which is 1. So again I have E into the surface area. The surface area of a spherical shell would be 4 pi r square. Remember, I have to take the area of the Gaussian surface and not the shell. And this is equal to the charge enclosed inside it upon epsilon naught. Now from here, if I rearrange, I get my electric field as 1 by 4 pi epsilon naught Q by r square. If you look at it carefully, this is same as the electric field due to a point charge at a distance r from it. This can also be written in terms of the surface charge density if you want, because this 4 pi r square is nothing but the area. So if I write the same expression in terms of the surface charge density, then this would be sigma by epsilon naught. This is the electric field at a point outside the spherical shell at a distance r from it. Let's look at the second situation. Now for the second situation, let's just assume that this point P lies on the shell. Now, if this point P lies on the shell, then small r would be equal to capital R. And in that situation, I can write my electric field as 1 by 4 pi epsilon naught Q by capital R square. So it is directly equal to kq by r square, which is the electric field due to a point charge. Now for the third scenario, when my P lies inside the shell. Now for inside the shell, my r would be less than the capital R. So in this situation, if I assume a Gaussian surface inside it of radius small r, in this situation also I will have to follow the same procedure, but by default I can tell you that the charge enclosed inside this blue shell is 0 because the charge lies on the surface of the shell. So there's going to be no charge inside this spherical shell that I assumed, or the Gaussian surface that I assumed. Therefore, the electric flux has to be 0, or in other terms I can say that my electric field is also 0 because the charge enclosed is 0. So for any point that lies inside the spherical shell, the electric field would be 0. So with this, we are done with all the applications of Gauss law, and now we move on to the next part of our video, where we will talk about the questions, the past year questions that have come in the board exams related to this topic. So let's look at our first question. It says that there's a charged sphere of radius r. It has a surface density sigma. The electric field on its surface is E. If the radius of the sphere is doubled, keeping the charge density the same, the ratio of the electric field on the old sphere to that of the new sphere will be. Now over here, this one is same as the electric field due to the spherical shell in over here. If I use the formula directly, then I know that my electric field is given by sigma by epsilon naught. So in the first scenario, if I talk about the surface charge density being sigma, epsilon naught is just the permittivity of free space. I can write down the second electric field as well. Now the radius is double, but the charge density is the same. So this will also be sigma by epsilon naught. If I take the ratio of E1 is to E2, then you can see that this will simply come out to be 1. Or in other terms, if you directly understand that the electric field in a charged sphere does not depend on the radius r when the surface charge density is kept the same, therefore I can directly say that the ratio of electric fields is simply 1 is to 1. It's a very easy direct question, so you should not be spending too much time on it. Let's move on to the second question. So an infinitely long straight wire having a charge density lambda is kept along the y dash y axis in the xy plane. We are supposed to find in the Coulomb force on the charge q at a point x comma 0. Now I know that the electric field due to an infinitely long straight wire, we have just derived it, the very first application we did, and we got it as lambda by 2 pi epsilon naught r. Now in our situation, the distance is x, so therefore my electric field expression would become lambda by 2 pi epsilon naught x. Now since I want to write down the force, my force would be charge times the electric field, so therefore the expression for force comes out to be q lambda by 2 pi epsilon naught into x. This is my expression for the force. Now, whether this force is attractive or repulsive, see, the surface charge density is positive and q is also positive. Since both of them are positive, so there would be repulsion between them, and hence option B would be the correct answer. Repulsive and lambda q by 2 pi epsilon naught x. See, in all these questions, we are directly using the applications that we have discussed before. Now, the next question, if the net electric flux through a closed surface is 0, then we can infer. See, if the net electric flux is 0, that means we have the charge enclosed by epsilon naught as 0. Obviously, the permittivity of free space cannot be equal to 0. So, it's obvious that my charge enclosed has to be 0. So, if from here, if I look at the options, no net charge is enclosed by the surface. This looks to be correct, but let's look at the other options as well. Uniform electric field exists between the surface. That's wrong. Electric potential varies from point to point inside the surface. That's wrong because it's an equipotential surface. And charge is present inside the surface. That is also wrong. So only option A is correct. Looking at our next question here, electric flux through a spherical surface shown in the figure is. Now I know that the electric flux is the charge enclosed by epsilon naught. Therefore, the only two charges that contribute to the flux are the ones that are inside the spherical surface, that is Q2 and Q1. So I will have Q2 minus Q1 upon epsilon naught as my final answer. Q2 is positive, Q1 is negative. I have directly taken the signs from the figure. So you just have to substitute. And moving on to our last question now. The electric flux through a closed Gaussian surface depends upon. Let's look at the options. No net charge, the first option, net charge enclosed and the permittivity of the medium, which looks to be correct because again, flux is Q by epsilon naught. So charge and permittivity of the medium. Net charge enclosed, permittivity and the size of the Gaussian surface does not matter. The net charge enclosed only, that's also wrong. And the permittivity of the medium only also is wrong. So the only option that is correct is A. So I hope you understood all the concepts that I taught you and you understood these questions as well. If you like my explanations and if you like the video, then please subscribe to my channel and stay tuned for the next video.